Hello, this is the final presentation of the article called Transactional Memory Coherence and Consistency within the scope of course parallel architecture. And I am Mehmet Sencer Altuntop. Let's begin. Well, this article is proposing a new system and they call it TCC, which is Transactional Memory Coherence and Consistency. Let's go with the introduction part. Shared memory can support simple program models. However, shared memory means complex consistency and cache coherence protocols. Consistency must provide rules for ordering loads and stores, trade-off between ease of use and performance. Cache coherence must track ownership of cache lines, requires low latency for small coherence messages. Highlights. A new shared memory model. This article offering us a new shared memory model. And they call it Transactional Memory Coherence and Consistency, shortly TCC. From now on, in the presentation, I'm going to call it TCC. So, latency of small coherence messages, unlikely to scale well. Interprocessor bandwidth likely to scale better. Message passing models can take advantage but hard to program. And we will have a system overview here. Well, when you design a system, you have to answer some of the questions here. If you end up well in this part, you may end up with a good system. So, question is kind of like this. Can we design a shared memory model with simple program model, simple hardware, good performance, and take advantage of available bandwidth? So, if we can end up good with this fourth question, then our system is something valuable. Basic TCC system. Transaction sequence of introduction that executes speculatively on a processor and completes only as an atomic unit. All writes are buffered only locally and only committed to shared memory when the transaction completes. Commit is atomic. Entire effect of transaction committed to the shared memory state at once. Transactions effect not visible to other processors until commit is performed. Processor broadcast entire write buffer in one large commit package. High broadcast bandwidth needed, latency not as important. Interconnect need not provide ordering. System-wide view, transactions appear to execute in commit order. Well, each processor must snap on commit packets to detect violations. Transaction detecting violation must roll back and restart. Register checkpoint mechanism needed. So, look at the drawing. In order to figure out that you have a violation, you need a register checkpoint mechanism. And at the time that you have a violation, you have to roll back and restart and re-execute with the new data. Consistency. Let's talk about this a bit. Other consistency models, ordering rules between individual memory references. TCC, sequential ordering only between transaction commits. All references from an earlier commit appear to occur before all references from later commit. Interleaving between memory accesses by different processors only allowed by transaction boundaries. Can provide illusion of uniprocessor execution by imposing original program's transaction order. Coherence. No ownership of cache lines. Writes are buffered. Invalidation or update only occurs by snooping commit packets. Don't rely on manual latency-sensitive coherence messages. Now, we will go with the programming model, and I'm gonna put myself here so that you can see better. Programming model. Programmer inserts transaction boundaries, similar to threading but no locks, less errors. One hard rule is transaction breaks cannot be placed between a load and subsequent store of shared value. Steps for parallelizing code with TCC. Step 1. Divide into potentially parallel transactions, such as loop iteration after function calls. Transactions need not to be independent. Dependence violations caught at runtime. Step 2. Specify order. And step 3. Tune performance. Database transaction processing. Most programs require ordering between certain transactions, and that is the problem. And the solution that the article proposing is assign phase number to each transaction. Only transaction from the oldest phase can commit and can implement barriers or full ordering. Timeline, as you can see, going up to down, and the barrier be mentioning is this, and the oldest phase is gonna commit for the first one. Performance tuning. Number 1, have to choose transaction. Large transaction amortize startup and commit overhead. Smaller transactions should be used when violations are frequent and minimize the amount of loss work. Number 2 is the TCC system provides feedback about violations to facilitate tuning. Hardware control transactions. Write buffer, as you can see here. Read bits, modified bits, optional renamed bits for L1 cache line. System-wide commit arbitration. You can see the face here instead of the numbers. Double buffering. Let's talk about this a bit. Double buffering allows a processor to work on next transaction while previous transaction waits to commit. Use additional write buffers and sets of read and modified bits. Well, without double buffering here and the transaction n and n+1, n+1 going in here when the first commit is finished. And with the extra write buffer, we can start the transaction n+1 here, which is before the commit before the request is ended and the first commit starts. And with the extra write buffer and read bits, we can start the transaction n+1 here, which is gonna increase the speed of our processor really good. Localization of memory reference. Hardware control transactions automatically divide program into transactions as buffers of overflow. Take full advantage of available buffer space. Programmer must still mark critical regions where transaction boundaries cannot occur. Automatically merge small transactions into larger ones. Input-output handling. Must guarantee no rollback after input is read. Obtain commit permission before reading input. If ordering of output is important, same idea. Request commit permission immediately. Well, simulation methodology. Optimal TCC model. Infinite bus bandwidth, no memory delays. Extracted parallelism well for many benchmark. Speed ups for automatically and manually parallelized benchmark with optimal TCC model.
And here you can see the explicitly parallel applications and the TLC Java applications. Limits of available parallelism. Most benchmarks needed 6 to 12 kilobytes of read state and 48 kilobytes of write state. Reasonable for current caches and on-chip write buffers. Most of the benchmarks requiring large read and write state can probably be divided into smaller transactions. Let's put myself here so make it simpler for you. Or maybe here. Yeah, that's better. Well, this table is showing us average bytes per cycles broadcast by one IPC system with an update protocol. And the red lines are the whole lines and the blue lines are the dirty data only. According to that, the results are like this. If invalidate protocol is used with 32-bit addresses, average of 0.5 bytes per cycle for 32 processors. For update protocol, up to 16 byte per cycles for 32 processor, and if only dirty data is sent, only 8 bytes per cycle. Other parameters. Snooping requirement significantly less than one address per cycle. Single snoop port per processor sufficient for up to 32 processors. Commit arbitration overhead compiler parallelized app were insensitive while performance suffered for apps with smaller transaction size. Extensions did not yield benefit in most cases. Extra read state bit per word rather than per line only mattered for few applications. Double buffering did not help. Will be useful when the bandwidth is limited. Well, conclusion part. TCC simplifies consistency and coherence. No need for rules for ordering individual memory references. No need for latency-sensitive coherence messages. TCC provides a simple and flexible programming model. Correctness is guaranteed. No error-prone locks. Tuning performance based on observed violation is straightforward. Uniprocessor ordering can be achieved by ordering all transactions. And an optimal TCC implementation extracts parallelism well for a wide range of benchmark. How about performance? Evaluation of a realistic hardware model necessary. Will be limited by broadcast bandwidth and commit arbitration overhead. Well, that was it. Let's put myself here because I'm gonna say goodbye. Thanks for listening. I mean, it's a like real thank you from my heart. If you could end up till here, I'm really happy to that. Have a good one. And before I close it, I want to say thank you for the lecture, Gülay, YALÇIN, and I'm Mehmet Sencer Altuntop. Have a good one, everyone.